Hello, so we're going to talk about passive transport. And we were talking about the cell membrane. And so we know that the cell membrane is what we call selectively permeable. It lets certain things in and out. Some things can go right through. If they're small, like oxygen can diffuse it can just go right through the cell membrane. If they're hydrophobic, they can pass right through that hydrophobic center. So hydrophobic nonpolar molecules can pass through. Large hydrophilic molecules, though, they're not going to get through. They're going to need some help. And we're going to talk about how we can get those things in and out of the cell. So passive, when we talk about passive transport, we're talking about moving things without energy. All right. So when we talk about without energy, we're referring to without ATP. And so we're going to use what's called a concentration gradient. And so with that concentration gradient, it means that when you have more on one side than the other, you have a partition. And so you can see here in my little picture, I have a high concentration here, and things are going to want to move to low concentration. It's kind of like playing pool. You know, you have all the balls in one spot, and as the game progresses, the balls spread out. Unless you suck at pool like I do, and you end up with just a hot mess on one end of the table, and people look at you like this game has taken an hour, move on. But ideally, it spreads out. Okay. So it's like when somebody sprays perfume, it spreads out. Somebody farts, it spreads out. Okay. So that's called diffusion. Okay. When we're moving things from high to low, and it does not require energy. Active transport on the other end, that is going to require energy, and that is going to go the opposite direction. So that is going to go against the concentration gradient. So it's kind of like this way is going downhill, and then going in this direction is going uphill. And so, you know, when you ride a bike, going downhill doesn't need energy, but going uphill does. And so the one that's going downhill is passive, uphill is active. So here is an example of some passive transport. So you guys know, you put a drop of some of us now are using those Mios or whatever. You put that in your drink and it will spread out. It takes a while. Most of us are impatient because we want to drink our drink. And so we'll use a straw and we'll stir it up. But if you sat there and let it go, it would eventually spread out and it would diffuse through the whole container. It's going to go from high concentration to low concentration. So what we have here is simple diffusion. So when we talk about simple diffusion, we always like start with time going in one direction. And so we have all these molecules out here, and over time we'll eventually get the molecules moving that direction. So each molecule is going to have its own concentration gradients, not dependent on other types of molecules. So what we're seeing here is this molecule is moving this direction because it's highly concentrated on this side. But this molecule here is concentrated on this side. So it's going to move in the opposite direction because they're going with their own concentration gradient. Okay. They're not dependent on each other. So facilitated diffusion means that we can move with the concentration gradient, but we need a little help. And so with this little help, we're saying that this molecule will not simply go through the cell membrane. So we're going to need some help getting through. But once we have help, we'll move on our own because we have a concentration gradient. And so we hear our helper is this little channel protein. And so it's going to open up an opening. And these are usually very specific for what they'll let through. And because we have a higher concentration, we're going to move into the cell. Now, in this case, we're going to talk about water. Water can diffuse across a membrane. And I know they're not showing water here, but they do talk about it here. Water can diffuse across the cell membrane, but it doesn't happen fast enough for chemical reactions because we need a lot of water. So we'll actually have these pores called aquaporins, which are very similar to this specific channel protein, but they're just specific for water. They'll let water in and out. So aquaporin, it's an integral protein, right? It goes all the way through. It is specific for letting water go in and out based on its concentration gradient. So these are some things that will affect the rate of concentration gradient. For one, if you have a higher concentration gradient, if your hill is steeper, you're going to move faster. Molecular mass, smaller molecules are going to move faster. Temperature, if temperature gets the molecules moving faster. So like if you, a lot of times we'll heat things up and it gets things move faster. Okay, so temperature will affect that. The solvent density, how thick is the cytoplasm? Are you swimming through water or are you swimming through molasses? Solubility, how well does it dissolve? Is it polar? Is it non-polar? How is it moving through the water, the aqueous solution there? Surface area, okay? If you have higher surface area, you have more space, will speed up diffusion rates. How, we can't, if our diffusion rate stays the same, but our distance is smaller, it will increase the rate because you're not going as far. And pressure. Okay, sometimes blood pressure will act as a force to force things through those cell membranes. So pressure as well. Plants will use pressure. Turgor pressure is another type of pressure. So when we talk about diffusion, we talk about diffusion as a substance moving from an area of high concentration to an area of low concentration. But when we talk about water moving according to its concentration gradient, we're going to give that a specific name. And that specific name is osmosis. So water will move down their concentration gradient from high to low, or it will follow the solute. So in this example here, I have a semi-permeable membrane, and notice I have all the solute here. Now I can say I have more water on this side per solute, or here I can say I have less water per solute. So the water is going to want to try to, because we want equal concentrations on both sides. It's like putting too much sugar in your coffee. I can't take the sugar out, but I can add coffee. All right, so I'm going to add the water to this side to try to get the same proportion of water to solute. And so this is called osmosis, moving water according to that concentration gradient. Tonicity. Tonicity is the amount of solute in a solution. So again, we're talking about the solution that's surrounding the cell. We are going to measure this with osmolarity. If you take chemistry, if you've taken chemistry, you know, you've learned about molarity, and that's concentration. So a cell will react to the concentration of the solution that is submerged in. And we have 3 different types of solution. You can put a cell in a solution that has the same osmolarity or the same concentration of solute, or you could put a cell in a solution that has higher solutes or lower solutes. And so that's where we get these words from. ISO, like isometric exercises, that iso or isosceles triangle means the same. That means you put the cell in a solution that has the same osmolarity, the same solution, the same salt or same solute, whatever's dissolved in the water has the same concentration. I always think of hyper next. I always like to do hyper next because hyper, you think about hyper, if you've ever been around hyperactive kids, right? Especially if you give them sugar after Halloween, they're bouncing off the walls, right? So hyper means you have a lot of sugar. Sugar is a solute. So if you have a high solute concentration outside the cell, that solution is hypertonic. And so what will happen is the water moves out of the cell to try to dilute the solute. Just think about it. Water follows the solute. So if it's high outside, it's going to try to dilute it. It's going to go out. The cell's going to shrink. Now, the last situation then we have is hypotonic. Now, hypo that's the only situation we have left. That means it's got a lower solute concentration, which means my cell has a higher solute concentration. So the water will come into the cell to try to dilute the solute. Remember, it's following the solute. So it'll go in, it will cause the cell to swell, and in some cases burst. So here is a picture of those 3 situations. So remember, ISO is the same. So we have, and water will move back and forth, but what we're saying is we have the same amount of water moving in as out. It's all equal. It's all good. But here, our hyper, remember, hyper means I have more solute out here. And so the water's going out to dilute the solute. And so, and you will have a little bit of water going in, but I have more, way more going out than coming in. And so my cells, my poor blood cells are going to struggle. That's not good. And then the other situation would be is if I had more solute inside my cell. So the water is going to go in to dilute the solute. And in this case, it can actually cause the red blood cells to burst. And that's called cytolysis or cytolysis, to break the cytoplasm, spews that cytoplasm out. Not good. We have the same situation with plants. So that was an animal cell. Animal cells don't have cell walls. So we have an additional structural support that will help us out here with plants. And so again, with our ISO, everything's good. Same amount of water moving in is out. Notice my central water vacuole it's okay. It's not big like over here. And when it's big like it is over here, because we're in a hypotonic, meaning we have more solute inside the cell. And this is what we want. We want that water to come in because the cell wall, well, when it's too full, the cell wall will say, okay, we've got enough water, we're good. But it makes the cells nice, and what we call it is turgid. And so it has turgor. I think it's turgor, sorry, pressure. And that allows our plants to be nice and erect and be nice and firm and look nice and healthy. The isotonic is, they're not quite as firm. They're kind of starting to get a little wilty over here. Oh, this is not good. This, my central vacuole is shrunk up. And not only is it shrunk up, but notice my cell membrane has pulled away from the cell wall, and that's called plasmolysis. And with plasmolysis, again, the cell membrane pulled away from the cell wall. And this is when my plant is referred to as being flaccid, or in our case, wilty. You know, your plants need to be watered. I'm looking at my plants now and they're a little wilty. They need water. All right. So ideally we want this situation for plants because that helps them to stay nice and firm. Then the next, so we had passive. So passive is where we weren't using any energy. We were moving with the concentration gradient. Sometimes we need to move against the concentration gradient. We need to be active. And to be active, we're going to go uphill. And so notice I'm moving, I have less concentration here, but I'm moving it into the more concentrated area. And so there are some situations where we need to set up a concentration gradient because we're going to do work with it. And we'll talk about how we're going to do some work with this in some other chapters. But right now you need to know in some situations, we need to either concentrate protons or we need to concentrate calcium or potassium or sodium. And these things are going to signal a change in your body, right? In one case, we're going to actually use it to make ATP, which is kind of weird to say, but we actually don't use ATP. We're going to use something else, but we're going to use active transport to make ATP in the electron transport in the mitochondria and the chloroplast. We also have a sodium potassium pump, which is going to set up an electrochemical gradient, which is going to work for nerve impulses and muscle movement. Right. So we definitely have to have active transport. We usually talk about the one active transporter that we'll talk about here. We'll talk about a proton pump, which is also another one later. But the one we talk about the most is the sodium potassium pump. And so with the sodium potassium pump, what we're doing here, and we can see our concentration gradients over here. Notice I have all this sodium. And so what I'm doing is I have a little bit in here and I'm going to actively pump sodium outside the cell and then pump potassium inside the cell. And in order to do that, I have to use ATP. It's kind of like a toll booth going through the old school. Those of us that are old enough to remember the old school tool boost before I pass, you got to pay your toll. And when it does this, it's going to move sodium out. It's going to drive potassium in. And then there's going to be a signal that opens up another channel that says, all right, go. And then they're going to diffuse back the other way. And that's going to send a signal for muscle movement with our nerve impulses. And you'll learn all about that in anatomy and physiology. And here, you should have been exposed to sodium potassium pump, active and passive transport. So we're giving you those building blocks for anatomy and phys. Sometimes we need to move some larger, and you'll do with that, talk about that when we go into digestion. So larger molecules, and those also require a lot of ATP, which is active. We're going to move against the concentration gradient, but we have this thing called endocytosis, and endo means to move into the cell. And there are three main types of endocytosis. We have phagocytosis, which takes in large particles. And we can see kind of like this puckering. It's kind of like this invagination of the plasma membrane, and then it will push down and then form that vesicle around that item, whether it is a macrophage, a white blood cell taking in a bacterial cell, or just your small intestine taking in large food particles, macromolecules. We also have what's called pinocytosis, which it takes in fluids. It's taking in liquids with some solutes, dissolved solutes. Does the same thing and invaginates here. And then we have what's called receptor-mediated endocytosis. And I think of highlight, remember the highlight with the, some of you guys, I'm showing my age right now. You had the little scoops and the wiffle ball and stuff. Well, this is kind of like having your little scoops. I guess now it'd be like lacrosse, right? So you have your little scoops here, and you will have a very specific molecule that will bind to it. And when you get enough of these bound, they kind of accumulate in one area, and then will invaginate, pinch down, and take that specific molecule into the cell. All three of these require ATP. They're all active transport. And this is again to move larger molecules into the cell. We also have the opposite. Sometimes we need to get rid of waste. And so we're going to do this by exocytosis. And so again, that vesicle is going to meet up with the plasma membrane. Remember, this is all phospholipids, so we'll uninvaginate and then dump its contents out into the extracellular fluid. And again, it requires ATP, which is why it's active transport. And that ends the lesson on passive and active transport, moving things into and out of the cell using proteins or with endo and exocytosis. I hope you found this was helpful, and I will see you in the next lesson.